Okay, so before I talk about combustion analysis, I'm going to go ahead and talk to you about something that hopefully you already know. It's empirical formula versus molecular formula. So empirical formula is the chemical compound. You basically are coming up with a whole number ratios of all the atoms that make up that compound. The molecular formula is the exact number of atoms that are in that compound. So that's an important thing to remember for empirical versus molecular formulas, because a lot of times in these combustion analysis reactions, they'll ask you for the empirical or the molecular or both. So the problem I'm going to do both. So to refresh your memory, a combustion reaction is a hydrocarbon plus oxygen producing carbon dioxide and water. Okay, now I didn't put in the states of matter, but your professor probably would. A hydrocarbon is always going to be carbon, hydrogen, and oxygen. And how we represent it when we don't know what it is CXHYOZ. So when you're reacting, or when you're doing a combustion analysis, you're trying to find out what the formula is for the hydrocarbon. And you can do this by knowing how much you have of the products. You will be able to determine that, because if you notice, there's carbon, carbon, hydrogen, hydrogen. The oxygen, we're going to assume the oxygen that's present here is coming from the hydrocarbon as opposed to here. Because we can't accurately account for how much oxygen is there when you react. Because unless you had a closed, sealed setup, you wouldn't be able, or environment, you wouldn't be able to determine that. And if you had a closed, sealed environment, more than likely the combustion reaction wouldn't happen. Because it would be basically a vacuum. So combustion can't happen in a vacuum. So, what I'm going to do is we're going to do a problem figuring out the molecular formula, or excuse me, the empirical and the molecular formula of caproic acid from a complete combustion reaction. Caproic acid is a hydrocarbon. It's the one that's responsible for the smell of goats, gym shoes, sweaty socks, just general stinkiness. And it is combustible. So caproic acid is that wonderful hydrocarbon that is the stink that I love so much. So what we have is we have in this problem, we have 0.450 grams of caproic acid. And in the products, in the reaction, the combustion reaction, we ended up with 0.418 grams of water and 1.023 grams of carbon dioxide. Now we're going to take that information and convert it to convert from moles to grams, and gram back to moles, and figure out the empirical formula, and then we're going to figure out the molecular formula. One last piece of information that's given to us is caproic acid's AMU, or molecular weight, is 116.2 AMUs. So that's what we're going to use at the very end. So the first thing we need to do is we need to convert from moles, or get to moles of carbon. So we're going to do moles of carbon, and then moles of hydrogen. So what we're going to do is we're going to take our moles of carbon, which we have 1.023 grams of carbon dioxide, and we're going to multiply that I'm going to move this over here to give myself a little bit more space. We're going to multiply that by a conversion factor, which is grams per mole. So in 1 mole of carbon dioxide, the molar mass is 44.01 grams. And then we're going to multiply that by a mole ratio. So for every mole of carbon dioxide, there's 1 mole of carbon. Okay? So we've got everything set up. We can cancel out grams of carbon dioxide, moles of carbon dioxide. So now all we need to do is do the calculation. 1.023 grams times 1 divided by 44.01 will give us 0.02324 moles of carbon. That's how many moles of carbon we have present in the carbon dioxide. Now let's do the same thing with hydrogen. So we have 0.418 grams of H2O, 1 mole of H2O is 18.02 grams. The conversion factor, so there are 2 moles of hydrogen for every 1 mole of H2O. So to make H2O, you have to have 2 moles of hydrogen to 1 mole of oxygen. We do the calculation, and we end up with 0.0464 moles of hydrogen. Okay? So there's our moles of carbon and our moles of hydrogen. Okay? I'm going to box that in because we'll need those figures in just a moment. I'm going to let you copy this down real quick. Okay, so if you need to, you can always pause and go back. So I'm going to erase this. Now, I've got moles, but I really want to get 2 grams so that I can figure out the empirical formula. So what I need to do to calculate the mass of just carbon, because remember, I'm just trying to find out carbon by itself, hydrogen by itself. So the mass of carbon and the mass of hydrogen, I'm going to do another couple calculations. So what I'm going to do is take that number, 0.02324 grams, or excuse me, moles of carbon, and then I'm going to multiply it by the atomic mass of carbon per 1 mole. Okay? And so what I do by that is I get rid of the moles, so I'm just multiplying that number by that number, which gives me 0.2791 grams of carbon. Okay? So that is our grams of carbon. So let's do the same thing with the hydrogen. 0.0464 moles hydrogen over 1. And so we have 1.01 grams of hydrogen in 1 mole. Oh, I didn't mean to mark through the number, just through the moles of H. So that gives me 0.04699 grams of hydrogen. Okay? You see how that works? All right. Now, we can use that to calculate how many grams of oxygen I have. But Dad, how do you do that? You're probably saying, well, how do I do that? How do I do that? Okay, here's how you do it. Remember the very beginning? I told you it was 4.5 grams of caproic acid. Well, if I take 0.450 grams and I subtract these two numbers added together, 0.2791 grams plus 0.0469 grams. I do that calculation. It's going to tell me how many, because that's grams of carbon, grams of hydrogen. It's going to tell me how many grams of oxygen I have. Okay? Because conservation of mass, you can't create, you cannot destroy, you can only change matter or shapes or states. So when you do that calculation, you end up with 0.124 grams of oxygen. Okay? So now I've got grams of oxygen, grams of carbon, grams of hydrogen. Last couple steps, we're almost there. We need to get to moles of oxygen. We need to find out how many moles of oxygen to be able to figure this thing out. Okay, I'm going to move this over here. 0.124 grams oxygen. Okay. All right. So I start off with 0.124 grams of oxygen. 16 grams of oxygen in 1 mole of oxygen. Cancel out that mole. Oh, I screwed up. What did I do? I flipped them. So 0.124 times 1 divided by 16 is going to give you 0.00775 moles of oxygen. Okay, starting to get a cluttered board, but we can still do this. All right, so I've got, in squares, I got moles of hydrogen, moles of carbon, moles of oxygen. I've got my grams. I'm going to need all of this information. So what I'm going to do is I'm going to take well, you know what, honestly, you don't need to worry about this after you've gotten this part right here helps you get to there. And that's really what you needed to be able to figure out the empirical formula. But I just want to tell you every single thing. So we have carbon. Well, let's do it this way. Carbon, we have 0.0234. Hydrogen, we have 0.0464. And then oxygen, I have 0.00775. And we need to divide these by something. Any ideas? You always divide by the smallest, okay? The smallest is going to be this. So 0.00775, 0.00775, 0.00775. So that means when you divide them, that's going to be C3 H6O1. So there's your empirical formula. That's your empirical formula. Now, but I also asked you to come up with the molecular formula as well. So the molecular formula, you're going to take that information up here to help you out. So if you were calculating the molecular mass of this, you would come up with 58.09 AMUs. If you take 116.2 and divide it by that, you get a factor of about 2, just a little bit over times 2. So multiply 2 times each one of these, and it's C6H12O2. That is your molecular formula for caproic acid. I know it's a long video. I'm sorry. I walked through every single step though for you. So hopefully this helps. You should be able to do it. I know you've got it in your brain. The stoichiometry, if you look over there, we're doing stoichiometry over there. So here's the thing. There's always going to be, if you're going from moles to moles, that's a one step. So you're going to have molar ratio as your conversion factor. If you're going on a two-step, if you're going from grams to moles or moles to grams, you're going to have two different conversion factors: molar mass, molar ratio. Molar ratio comes from the balanced chemical equation. The first step, the first thing you have to do is balance the chemical equation. Once you've done that, everything else is easy peasy. A three-step conversion is probably the easiest to set up. You're going from grams back to grams. Always, 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 it's going to be grams, molar mass, mole ratio, back to molar mass, and then grams. So let me show you. That's kind of how I set it up. If you look, that's a problem. Blue is the given. Given goes up in the top left-hand corner. Unknown goes in the top right-hand corner. And you can see how we use the molar ratio. So KClO3, potassium chlorate, is the blue or given. O2 or oxygen is my unknown. So that's why it's in red. And you can see my conversions. If I started off with grams, same thing, just different order for the conversion factors. And if there were if I was asking for from grams to grams, then I would have one more set of boxes for molar conversion. Okay, just make sure that you're doing the units cancel each other out. Okay, see how they cancel each other out? That's all you need to do. You got this. Love you.